We're going to cover lesson 76, and lesson 76 has so many pieces. It's a long section. We have several trig identities in this section. I am going to print an attachment with all the identities, but we're going to talk about how they're derived, how to use them. So there is a lot in this section, so hopefully you're watching. So functions of negatives. So let's review a few things. For example, whoops, that was kind of sloppy. The function of x, if I write negative f of x, and then the function of f of x, f parentheses negative x. So both of these are a type of transformation, and both of them are reflections. And so we're going to review what types of reflections both of these create. So the first a vertical reflection. So if I had, for example, a parabola as a perfect example, then it would reflect it down. The reflection occurs up and down because it is vertical. Now, if the negative is in the parentheses, if it's inside next to x, then it affects our x values. So this bottom one creates a horizontal reflection. So, for example, if I had y squared, then a horizontal reflection would look like this. Now, 76.A goes over, kind of reviews what we know about symmetry. So if I have an even function, for example, x squared, x to the 4th, x to the 6th, if it is even, then the graph will be symmetric across the y-axis. Now what that means, because it's important that you understand, so if I have a parabola, symmetrical across the y-axis means that if I was to record this point on the right, both x and y are positive. The point on the left, my y value doesn't change. It's my x value that is being changed. And so the y value remains the same because it's symmetrical across your y-axis. Now, an odd degree function, for example, x to the 1st, x to the 3rd, x to the 5th, and so on, will be symmetrical across the origin. So it's symmetric across, well, I should put about, symmetric about the origin. So for example, if I have a cubic function, it looks like this, and its point up here on the right, I'd have both x and y, and they'd both be positive. But the point on the left, notice what quadrant I'm in, both of them will be negative. So it's across is 0. So it goes over to introduce us to some trig identities. So for example, if I have the sine of 30 degrees and the sine of negative 30 degrees. So we're going to find both, and then we'll talk about the three trig identities. So the sine of 30, if I was to draw my 30, 60, 90, right here's my 30-degree angle, 1, 2, root 3. So the sine of 30 is 1/2, right, because I am in quadrant 1. The sine of negative 30, right, is moving clockwise, which would put quadrant 4. And all students take calculus, sine would be a negative 1/2. They both have 1/2, but the sign of your negative degree is negative. And so this introduces us to the first trig identity, and that is that the sine of a negative theta is the equivalent to -1 times the sine of the same angle but positive. So the sine of negative 30 degrees is -1/2. That's equivalent to the sine of 30 times negative 1. Okay, so that's the first trig. I am going to highlight them, and we are going to use them. So, for example, if the sine of 150 equals 1/2, then the sine of negative 150 would equal negative 1 times 1/2, which is 1/2. So that is what that property or that identity is telling us. Now, this is different for cosine. So, for example, if I have to find the cosine of 30 degrees and the cosine of negative 30 degrees. So, here's my triangle, right? And let's see here. Wait, and I should have done this all, because we'll use this students take cap. So, here's positive 30. Here's 30 down here. So cosine, right, of 30 degrees would be adjacent, so root 3 over hypotenuse, which is 2. The cosine of negative 30 degrees is the same relationship, it's just whether it's positive or negative. And all students take calculus. Cosine is actually positive in the fourth quadrant. So based on this data, my second identity is that the cosine of theta is equal to the cosine of that same degree in the negative direction. And so this one is because cosine is positive in the fourth quadrant. Moving on to the tangent. So let's say I asked for the tangent of 30 degrees and the tangent of negative 30s. So same triangle, right? It's just that tangent is opposite over adjacent, so 1 over root 3, and we're not going to rationalize it. And negative 30 would also be 1 over root 3, and tangent is a negative. So tangent creates the same identity that sine. The tangent of, the tangent of negative theta is equal to negative 1 times the tangent of positive theta. And so those are our first 3 identities. And so I've highlighted these because we are going to use them in later sections. So moving on to 76 point B. And they titled this in the book, Functions of the angle. And I don't know why they titled it that. Sorry, my pen is running out. Grab a new one. I'm not sure why they called it that. This should be called the Cofunction Identities. That's what it should be called, because it introduces you to all of them. So here is what it goes over. First, let's start with review. Complementary angles mean they add up, so complementary angles add up to equal 90 degrees, right? And so complementary angles add up to equal 90 degrees, right? And so let's go over triangle. This is the basis of their property, and then I will go over. So in any right triangle, if I label the acute angle as theta, then to find the other angle, if this is 90, well, 180 minus 90 is 90. So this angle here be labeled as 90 minus whatever theta is. And so I'm going to label my sides A, B, C, so you can see how this identity works. So the sine of theta equals side A, B. The cosine of 90 minus theta, so this angle, is also A over C. So they determined that sine and the cosine of its complementary angle are equal. So this property would be that the sine of theta is equivalent to the cosine of its complementary angle. And so sine and cosine are referred to as cofunctions. And so here is maybe a better example. Side is 5, 10, 5, 3. This is 30, 60, 90. So in this example, the sine of 30 degrees, according to this identity, should be equivalent to the cosine of 60 degrees because these angles are complementary. The sine of 30 equals 5 over 10, which equals 1/2. The cosine of 60 is also 5 over 10, which equals 1/2. So cofunctions using complementary angles are equal. So I'm going to write down all of our trig identities. So our cofunction identities. The sine of 90 degrees minus theta is equal to the cosine of theta. Now the same is true in reverse. The sine of theta is equivalent to the cosine of 90 minus theta. Now sine and cosine are cofunctions because of the co. So sine, cosine. Just like tangent and cotangent. And secant and cosecant. See how these, so these are your cofunction pairs are right here. These are your cofunction pairs. And I wish you were here in person because this is harder to learn. All right, so moving on. So that's the first pair. Now let's do the tangent of theta is equal to the cotangent of 90 minus theta. The cotangent of theta is equal to tangent of 90 minus theta. The same will be true with the other pair. So the secant of 90 minus theta will be equal to the cosecant of theta. And then last cosecant of 90 minus theta will be equal to the secant. And so there are 6 of them. These are all identities. So we're going to use them to complete the following. So we're going to evaluate the following based on just. So number 1. What is the sine of 38 minus the cosine of 52? Crazy, right? All right, so neither of these are in our 30, 60, 90 triangles or 45, 45, 90. However, using a calculator, I know that 38 plus 52 is 90 degrees. So I know that 38, and I'll do a different color. So I'm going to rewrite this, and you can do it either way. You can make them both cosine or both sine. It doesn't matter. So I'm going to write this. The sine of 38 degrees minus, I'm going to rewrite this. This is equivalent. The sine of 90 minus 52. Right? The cosine of an angle is equivalent or equal to 90 minus that angle. So now I'm going to simplify. That gives me the sine of 38 degrees minus the sine of 30 degrees, which equals 0. Next one, we're going to evaluate what is the cosecant of 10 degrees divided by the secant of 80 degrees. Now, all of these, notice they don't want you to use a calculator. So this is without a calculator. a calculator using the identities, being able to manipulate them. So cosecant and secant are cofunctions, and I know that 10 plus 80 is 90, so I know these are complementary. So I could rewrite either of these. It's just a matter of which one I want to rewrite. So I know that the secant of 80 degrees is equivalent to the cosecant of 90 minus 10 degrees. Okay? Because they're complementary. Sorry, this should say secant. So now the secant of 80 degrees is equivalent to the secant of 80 degrees, which is 1. And I'm using that based on this. I know the cosecant of theta is equal to the secant minus that angle. So I know that cosecant of 10 is equivalent to the secant of 90 minus 10. So I think we'll move on to this next part where you are writing the equivalencies. So I think this is number 3. Complete the following. So part A, the cosine of 35 degrees is equal to what? The tangent of 72 degrees is equal to what? The cosecant of x plus 20 is equal to the secant of 25. So solve for x. And then let's see here, last but not least, the cotangent of pi over 2. All right, so we're going to complete these. So the cosine of 35 degrees is going to equal the sine of 90 minus 35 degrees because they are cofunctions, and so I'm looking for the complementary angle. So the answer with this equivalent to 90 minus 35 is 50 degrees. So the cosine of 35 has the same side ratio as the sine of 55. So tangent of 72, tangent and cotangent are cofunctions. So I would write the cotangent of 90 minus 72 degrees. So that would be equivalent to the cotangent of 18 degrees. So these two have the same answer. All right, here. So I have the cosecant. Well, this is saying that this angle and this angle are complementary because they're so x plus 20 plus 25 equals 90. So if I subtract 45 from 90, x equals 45 degrees. Right, because these should be complementary. The cotangent of pi over 2 would equal this should be tangent. Would equal the tangent of pi minus pi over 2, which would give me the tangent of pi over 2. So that is using those identities. We can do one more just for the sake of it. I'm looking at my examples from last year. The sine of 9x over 2 equals the cosine of 15 degrees plus x over 2. Solve for x. So I know based on what we've learned today that these angles should be complementary. So 9x over 2 plus 15 plus x over 2 equals 9 degrees. The 15 and add these fractions. So 10x over 2 equals 75, which would give you 5x equals 75, which would give us x equals 15. All right, I think you've had enough of that. Let's move on. 76 point D doesn't really cover, point C doesn't really cover any. It just talks about what trig identities are. So there's nothing in here to go over. Last part of this section is 76.d, where we get into some more trig identities. Okay, so rules of the game. Is proving an expression true using trig identities. So we're going to go over some more identities, and they are the reciprocal identities. And there are a couple for tangent. So before I get started, let's go over what we know, okay? So on this side, I know that the sine of theta equals opposite over hypotenuse. I know that the cosine of theta equals adjacent over hypotenuse. And I know the tangent of theta equals sine of theta over sine of theta. Now I can go over why, but I doubt that you care. But this is a big identity that we're going to use. Now let's go over our reciprocal identities. This states that the sine of theta is equal to 1 over the cosecant of theta. And the opposite is true. The cosecant of theta equals 1 over the sine of theta. So sine and cosecant are reciprocal functions. Try not to get confused. There's inverse function, inverse trig functions. There is cofunction pairs, and now there's reciprocal functions. They are reciprocal because the sine of theta is opposite over hypotenuse, and the cosecant is the hypotenuse over opposite. So the next cosecant of theta is 1 over the secant of theta, and the secant of theta is 1 over sine of theta. The last pairs, and tangent can be written two ways. The tangent of theta is 1 over the cotangent of theta, or the cotangent of theta equals 1 over the tangent of theta. But a more important one is the tangent of theta equals theta. I wrote it up above. So the cotangent of theta is the reciprocal. It's the cosine of theta over the sine of theta. Sorry. So they're all important. So I'm going to highlight all of them so that you can see all of them. They will also be on your trig identities sheet. We're going to work on proving an expression true using all of the identities that I've highlighted in this section. So I highlighted these 3. There are these 6, and then there are these. I should not have highlighted these a different color because I don't want people to confuse the trig identities with what I did earlier. All right, so number 1. Show the following is true using trig identities. And there's more than one way to do this, but we're going to do the ones that maybe are the fastest. So number 1, we are going to prove that the cotangent of n of x over the cosecant of x is equal to the cot of x. So here I go. I'm going to rewrite cotangent. I know that cotangent is the cosine of x over the sine of x. And then I'm going to write over. And then I'm going to replace cosecant with its reciprocal function. I know that cosecant is 1 over the sine of x. So I've replaced both. Now it's the top cosine of x divided by 1 over the sine of x. Now, when we divide, we multiply by the reciprocal. So the cosine of x over the sine of x times the sine of x over 1. Notice I switched the division and flipped the second fraction. These then cancel, and I'm left with the cosine of x, which is what we wanted to prove, and we are done with that one. I know, these are kind of crazy. They take a lot of practice. So number 2, show that the sine of x times the cosine of x equals 1 over the secant of x. So let's quickly talk about, I know that the secant is the same as the cosecant. Like, these are reciprocal functions, secant and cosine. And so let's just be able to, like, I know that the cosine of x is equal to 1 over the secant of x. This is what I know based on the reciprocal identity. So I need to somehow get rid of the sine of x, right? I need to eliminate that in order to prove that this is true. So what I did, and maybe I wrote, I wrote this down wrong. This should say cotangent. Makes sense. Let me rewrite this. Sine of x times the cotangent of x equals 1. And I know that this is true. So I'm going to rewrite. I'm going to bring down the x. I'm going to rewrite the cotangent of x. I know that cotangent is this as cosine of x over the sine of x. Now, if I look at that, I know that these would cancel, and I'm left with the cosine x, which is equal to 1 over secant of x. I know, pretty crazy. All right, next one. Show that the cosine of negative theta times sine of 90 minus theta is equal to cosine squared of theta. So as soon as I see this, I think, oh, okay, I know the cosine of theta times the cosine of theta would equal cosine squared theta. So I need both of these over here simply equal to cosine of theta. And so these are the first identities we went over. So the first 3 that we highlighted was that the cosine of theta is equal to the cosine of negative theta. And so that's the first one I'm going to replace. I know that this is equal to the cosine of theta. And then based on these identities, I know the cosine of theta is equivalent to the sine of the complementary angle. So I know that this is equivalent to the cosine of theta. Based on those identities, I know that both multiplied would give me cosine squared theta. All right, next one. The sine of 90 minus theta times the secant of 90 minus theta is equal to the cotangent of theta. All right, so let's start with our cofunction identities. I know that this is equivalent. Sine and cosine are cofunctions. And I know that this is equal to the cosecant of theta. So now I have these, right? And you're kind of like, how the heck am I going to get my cotangent? Watch this. I'm going to bring this down. And I'm going to rewrite the cosecant. Cosecant is the reciprocal of 1 over the sine of theta. And then I'm going to multiply these straight across, and I get the cosine of theta over the sine of theta, which happens to equal the cotangent of theta. Next one. Cosecant of 90 degrees minus theta times the cotangent of theta equals cosecant. Whoops. All right. So let's rewrite these using our cofunction identities. That's what I think of when I see 90 minus theta, is I would go look at these. Okay, I know that cosecant of theta is equal to the secant of 90 minus theta. So I know that the equivalence to this is the secant of theta. And then I also know that I can rewrite the cotangent of theta to be cosine of theta over sine of theta. Okay? Now, from here, I'm kind of like, okay, how do I get this to equal cosecant? Well, I know that the cosecant of theta equals 1 over the sine of theta. So I need this side to just have 1 over the sine of theta. So I'm going to rewrite this guy to be 1 over secant and cosine are reciprocal functions. And these cancel, and I'm left with 1 over the sine of theta, which equals the cosecant of theta. Whew, I know that's all crazy, but use the note and use the sheet tab. 76. You're going to skip numbers 3, 5, 17, and 26. Thank you.